Let's solve the following problem. You're given a conducting sphere of radius 5 meters. On that sphere is placed 10 to the minus 8 over 9 coulombs, and you're asked to find the electric potential field everywhere. We always start by drawing a figure. Here is our 5-meter radius sphere with charge on it and the corresponding electric field intensity. We need to find the electric field intensity in order to find the potential field. The charges all repel and go to the surface of the sphere, and there's no charges inside, and there can be no electric field inside, otherwise you'd have current flow. So the electric field is 0 for r less than 5 meters. If you were given a hollow sphere instead of a solid sphere, the electric field intensity everywhere inside would still be 0. To convince yourself that the field is 0 everywhere inside, go back to the situation where the sphere was solid and then think about what would happen if you removed material from the inside, that you were able to transport some of the material inside out of there. Nothing would change, and so you would still have a 0 electric field inside. By now you should be getting comfortable enough to just write down the electric field intensity for r greater than 5. It's whatever charge you've put on the sphere divided by 4 pi epsilon sub 0 r squared, and it's in the radial direction. If not, go ahead and pick a Gaussian surface that is a sphere of radius r, where r is greater than 5 meters. Find your electric flux density field, and then divide by epsilon sub 0. Another thing I'd like to point out is keep the charge fixed, but reduce the radius. You would see that the electric field intensity outside the sphere would not change. And this is essentially the electric field intensity due to a point charge Q at the origin. So the field outside the sphere is no different than that of a point charge. So if you're outside the sphere, you can't tell if you have a sphere of some radius with a charge Q on it or a point charge Q at the origin. Let's put our charge in of 10 to the minus 8 over 9 coulombs and put in our value of the permittivity of free space. 4 pi over 36 pi is 9. These 9's cancel, giving us 10 over r squared in the radial direction. A farad is a coulomb per volt. We'll get to that later when we talk about capacitors. The coulombs cancel. If you put r in meters, you'll have meter over meter squared times volt, so the units are going to be volts per meter. So now we have the electric field intensity everywhere. The potential field is the amount of work to move 1 coulomb of charge from infinity to r, which you obtain by minus the integral from infinity to r of E dot dl. So your mental representation should be 1 coulomb times the electric field is the force on 1 coulomb, and a force times a distance is an amount of work. So let's first find the potential field for r greater than 5 meters. When r is greater than 5 meters, this is our electric field intensity, so let's substitute it in. A sub r dot dl, you're only doing work when you're moving in the dr direction. The integral of dr over r squared is minus 1 over r. And our electric field is volts per meter. dr is in meters, so our result will be volts. So we evaluate at our limits of integration. So for r greater than 5 meters, our potential field is 10 over r volts. Now let's find the potential field for r less than 5 meters. Now a common mistake that is made is that the electric field intensity is 0 for r less than 5 meters, so students will conclude that the potential is 0 for r less than 5 meters. That is not correct. We still have to apply this equation for when r is less than 5 meters. Our function for the electric field intensity is different when r is greater than 5 meters than when r is less than 5 meters. So we'll integrate from infinity to 5 meters of 10 over r squared, and then we'll integrate from 5 meters to r of 0 dot dl, because the electric field is 0 for when r is less than 5 meters. This integration is 10 over r, and our limits of integration are infinity and 5 meters, and this integration is 0. So the result is 2 volts. Let me collect our two results and then we can discuss them. This represents the amount of work to move 1 coulomb of charge from infinity to a particular r location. So the amount of work is increasing until you hit the sphere. Once you get to the sphere, it takes no more work when you move inside the sphere because there's no electric field intensity in the sphere. To get to the sphere, it takes 2 joules of work. So once you're inside the sphere, the potential stays constant at 2 volts. The sphere is an equipotential object. Let's compare this to gravitational potential energy. Let's say you're walking up a slope to the top of a hill that has a flat top. So it takes an amount of work to climb to the top. Once you're at the top, your gravitational potential energy does not change as you walk around. Your gravitational potential energy is still the amount of work it took for you to climb to the top of this hill. It's the similar thing for moving 1 coulomb from infinity to your sphere.